Evaluate the following integral. Let's say we have an integral that is e in exponent x squared dx. Sometimes we can express some function in terms of the Maclaurin series. And for instance, we have the function f of x is equal to e in x is as follows. Ex is equal to 1 plus x, we write in the expanded form as a series of Maclaurin. And it gets 1 plus x squared over 2 factorial plus x cubic 3 factorial, etc. But the finite term of this function can be x in n over n factorial. And if we write this function, this expanded form, as a sum series, we have ex is equal with the sum n from 0 to infinity xn over n factorial. And now if we take some comparison with the ex squared, whenever is x, we are substituting x squared. For example, here, instead of x, we substituted x squared. If we have, for example, function ex squared. Then, if we have here x squared, is x squared instead of x, times the 2 here is going to be x4 over 2 factorial. And x squared times 3 is x in a 6 over 3 factorial. And instead of this x squared times 4 is x8 factorial over 4 factorial, and it's going to look at something like this. For example, ex squared, when we are substituting instead of x everything, so ex squared, we get this series. And we already know that a finite term that can generate all these terms here is x in exponent to n over n factorial. And if we write this series in the term of the sum, we can write ex squared is equal with the sum n equal to 0 to infinity x to n over n factorial. So let's integrate the last finite term, this term here, x to n over n factorial instead of ex squared. And what we're gonna get here? So instead of integral ex squared dx, we are taking just the finite term, and we are integrating just the final term. And here is some integration, what we did on the side. And if we take x to n over n factorial, and this 1 over n factorial we are factorizing, we get in front of the integral, and inside stand just the x in exponent to n dx. And now, if we are writing this, the factor 1 over n factorial is right here. And now, if we integrate x in exponent to n dx, this now is elementary integral, and we can get x to n plus 1 over 2n plus 1 plus primitive c. So, and when we multiply everything, those are two fraction expression as a fractions as it looks. So in the end, the result of the finite term is going to be x in exponent to n plus 1 over n factorial times 2n plus 1 plus c. But we already know it was just the last term, but if we write the whole Maclaurin series, for example, when we wrote ex squared, and if we write it as a whole function, then integration of ex squared dx is going to be with the sum of n from 0 to infinity x to n plus 1 over n factorial to n plus 1 plus c. On the other hand, this is the final result, what is going to be, but sometimes when we are looking, for example, in some calculators, like Wolfram Alpha or Symbolab, those calculators are not going to give us this result, but they're going to give a different result, and we are going to justify what are those different results. In mathematics are known as those error imaginary functions, or sometimes a Gauss error function they call, and one of the results that can be of the error imaginary function is this result here. 2 over square root of 2 pi, and the sum of n equal to 0 to infinity z to n plus 1 and factorial to n plus 1. So, and this is expanded form. But here we taking just this part, and we are comparing with the result what we got here, and just the sum, if you look at the sum, is a similar, is the same, is very similar with this sum here. But now we are going to do some calculation here in the next. So what we are taking here, we are taking just this part of the function, of the error function, and now I took just this part, but instead of a z, let's write x, error imaginary function, 2 over square root of pi from n equal to 0 to infinity x into n plus 1 over n factorial to n plus 1. So what we're doing here, we are multiplying with this reciprocal, so we want this here to simplify in the front, and when we multiply all of this equation here, what we have now, with square root of pi over 2, we get a square root of pi over 2 times er fi x is equal now with a sigma n from 0 to infinity x to n plus 1. So we have this expression, so I don't have to read everything to not waste the time. But now this part here is similar with the part what we got the result from the function ex squared dx. So if we are looking, if we are comparing this result here now, and this result are the same. But now in the result of the function ex squared dx, instead of the result here, I am going to substitute for this value here, the square root of pi times error function, imaginary error function of x. So, and if I'm substituting instead of this here, this part, then finally we get the integral of ex squared dx is equal to the square root of pi over 2 error imaginary function plus c. So the calculator, when you look, for example, for this result, for this integral, you are going to get this result in the calculator like alpha, like Wolfram alpha or symbol lab. And in the end, this is what you get the result, and it's justified how it came. But in the end, just I'm showing you and the graph how it looks at those error function. For example, this is the graph of the error imaginary functions.